All right then. So can I start?
Yes, you can start.
Okay. So just a minute. Yeah. So hello everyone. I am Vasundhara. I am working right now as a PhD student at Daisy with Andrew Taylor and Aryan. And Aryan is actually already present there. And I'm going to be talking about the work that I've been doing in my PhD, which is basically ultra energy cosmic rays and galactic halo bubble. And this pretty picture that I have here is what I'm going to draw your attention to. So, what do I mean by galactic halo bubbles? Well, basically, galactic halo bubbles in this context is an all-encompassing term for the Fermi bubbles shown in red here, which are non-thermal, and the thermal E Rosita bubbles. And together, I call them throughout this talk as galactic halo bubbles. And what I'm interested is actually studying magnetic fields in these galactic halo bubbles. But first, the question begs are these bubbles exclusive to Milky Way, or is it been seen in other places? And of course, we have external galaxy observations, like I show you here. On the left is NGC 253 in X-ray, and on the right is NGC 253 in radio. And you can see that such extended emissions are not uncommon. However, you see them mostly in starburst galaxies, and our galaxy is not a starburst galaxy. So of course, it makes it interesting why such bubbles exist. Of course, it's important to note that if you have such large-scale structures, then that implies that you will also have large-scale fields. And if you visualize like a caricature of our galaxy, so here we have the bubbles in the center, and then you have the galactic disk, and you have a large galactic halo, and you have some extra cosmic rays, extra galactic cosmic rays coming into the galaxy. Um, you know, as also mentioned in the previous talk, that if the galaxy is in equipartition, then roughly the the energy density in the gravitational pressure, in the thermal pressure, in the cosmic rays, all of these pressures are roughly around 1 eV per cc. However, of course, we do not have accurate estimates of these energy densities, at least for magnetic field, in both regular and turbulent components, and these numbers are mostly motivated by extragalactic, so external galaxy observations. So what is one way of probing magnetic fields in the galactic halo? So one of the ways would be looking at synchrotron, and synchrotron requires two ingredients: magnetic fields and a non-thermal electron distribution. So first, let's look at magnetic fields. Um, so our magnetic field model is something very simple. It's a toroidal field which has radial and azimuthal cutoff, which is a free parameter. So this Z mag and R mag. And the strength of the field is also a free parameter. And the field reverses directions above and below the galaxy. So basically, it's a very simple toroidal magnetic field, which was also being motivated by rotation measure observations. And along with, of course, a structured field, we have turbulent fields. And you need turbulent fields because, I mean, when there is an outflow, there is turbulence. And hence, we choose a very simple 5/3 Kolmogorov spectrum for the turbulent fields. And we choose a turbulent field configuration such that each mode has almost the same power. So the strength of the turbulent field is our fourth free parameter in our model. And then, of course, once we have the magnetic fields ready, we need a non-thermal electron distribution. And we chose this very simple exponential cutoff for the electron distribution. So this is what is also called the WMAP electron distribution. And the two free parameters that you see in the electron distribution are the radial and the azimuthal cutoff. However, the cutoff for the electron distribution and the magnetic field has been kept the same, since if you don't have electrons present, then you cannot, if you don't have electrons present and you have magnetic fields present, you can still not see synchrotron. So the synchrotron requires the presence of both. So hence the cutoff has been kept the same. So now we have all the ingredients. what do we look? We look at synchrotron radiation. This is a very standard picture of polarized synchrotron emission, which most of us have seen, say probably from Rybicki and Lightman. So you have you have magnetic fields and a distribution of electrons. And of course, you're always sensitive to, you always see a projection of your emission. So that's what's the plane of the sky, and you see the projection in this way. But I find another way of visualizing this polarized, synchrotron radiation in a different fashion, and that is through ellipses. So we suppose we have an emission of electron, distribution of electron emitting synchrotron radiation, and we can visualize each emission sort of like along the line of sight as an ellipse, such that the major axis of the ellipse is the perpendicular polarization and the minor axis is the parallel polarization. Of course, this minor axis is also parallel to your B perp, which is the line of sight perpendicular field. I mean, I know I can understand this sounds a bit mouthful, but what I'm trying to motivate is, depending on how your ellipses are oriented, you are going to be either be observing polarized synchrotron emission or unpolarized synchrotron emission. In our case, we were interested only in probing polarized synchrotron emission. So with the 5 free parameters that I mentioned to you before, I ran an extensive scan to find the best fit model. So what I choose, so to compare our model with the data, we choose the Planck data at 30 gigahertz, because Planck at 30 gigahertz in the polarized regime is mostly synchrotron dominated. And you can see that I have created several cuts in this sky map. The reason being that, first of all, we are only interested in the galactic halo bubble region. So anything beyond 90-degree longitude was not something that we were interested in. And since we are not interested in modeling the disk, we cut out the disk. The third cut that we made in this was the cut for the North Polar Spur. And the reason being is that some of us might know that North Polar Spur has been a topic of debate between starlight polarization and the X-ray community for a while. And there are recent papers which suggest that at least parts of the North Polar Spur might be local. And therefore, we motivated this cut based on previous observations, and we basically made sure that all the comparisons that were done including these cuts. We also do a 15-degree Gaussian smoothing, and the reason for that is that we were not interested in probing the turbulent part of the magnetic field. So basically, we are washing out quite the micro features that might arise from the turbulence. So then we obtain a best fit, a set of best fit parameters. As you can see, our turbulent field is barely constrained, which was something we expected. And we find a somewhat constraint. We find a constraint on the structured field and also on the radial and the azimuthal cutoff of the magnetic fields. So once we have these constraints with us, we did backtracking of ultra high energy cosmic rays using CR-Propa3. And what we find is we chose nitrogen as a species of particles, and the rigidity was 40 eV, and all of this was motivated based on Pierre Auger's observations. So we chose 2 sources, Sene and NGC253, and we start with the isotropic distribution of cosmic rays from Earth, and we backtrack them till a certain observation sphere or termination length. And then we look within a 5-degree region for the arrived cosmic ray positions. And you can see with the orange blob and the green blob and compare it with Auger's latest results, that they are somewhat similar. The solid dot that you see on the sky is actually the coherent deflection of your cosmic rays. So it's like the average deflection direction of the cosmic rays. And this is a useful quantity if you want to compare our model with existing magnetic field models. So we chose the well-known Glennis-Farrar model, but for Glennis's model, for the JF12 model, or as it is called, we only turned on the the toroidal halo part of the magnetic field. And of course, the turbulent field was turned on. And we do a set of comparisons. So you can see that in the JF12 model, this coherent shift or the shift of the cosmic rays from the original source position is far greater than what is seen in our model. And this basically links to a couple of things. One, if you have stronger structured fields, this coherent deflection would be much stronger, and that's what's seen in GF12. And if you have stronger turbulent fields, then you will have more spreading of cosmic rays. And that is what is seen from our toy model. Another thing to note is that for these sources, you are not going to be disk dominated. So both SENE and NGC253 are quite further away from the disk. So even if you include the disk within your cosmic ray propagation code, the deflections will not get deflected, and we did the check for that. So this is why disk is not important. One last thing that I would like to highlight here is that, of course, you can, in comparison to Auger's results, the JF12 model tends to deflect at least for NGC 253 quite further to quite to higher latitudes, the cosmic rays. That being said, yeah, so I'm close to my conclusion. So what we find is that from our synchrotron calculations, that we found that the best fit value for the total magnetic field strength was roughly around 7 microgauss. And the spatial extent for the halo height was roughly 6 kiloparsecs, which is also what other observations in SPAS suggest. The arrival directions of cosmic rays, of course, is highly tangled with the strengths of structured and turbulent fields. Excuse me. And this is what we also see that, and when we compare our model with Auger, we see reasonable agreement. For the future, of course, it will be interesting to look at rotation measure data from MeetCat and FAST, which would be available next year. And similarly, we can use CBAS and LOFAR for the future. I'm sorry for my coughing. I was sick for the past week. So yeah, sorry.